In the previous session, we had seen one kind of multiplication of vectors which yields a scalar product, that's dot product, right? So there is another kind of multiplication, vector multiplication, as I said, it's called cross product, okay? Because the operator that we use is cross, and the result of this particular multiplication will be another vector. Multiplication of two vectors will yield another vector, so it's also called the vector product. Okay, so suppose there are two vectors a and b. The cross product of those two vectors a and b is another vector. Okay, it's another vector whose magnitude is equal to the product of the magnitude of a, the magnitude of b, and the sine of the angle between them, the sine of the smaller angle between them. So that only defines the magnitude. So when you say a vector, it, along with the magnitude, it also has got the direction, right? So its direction is in the direction of a right-handed screw as a is turned into b. So if you place a screw at the point of intersection of both the vectors, and if you move the screw in the direction of from a to b, the direction of the screw will give you the direction of the product vector. Okay, just like you have taken the third coordinate, when you consider three coordinate system, when you take x and y, right, what is the direction of z? So we have taken the example of a right-handed screw and determined the direction of z. Similarly, to find the direction of the product or cross product of two vectors, you can use the right-handed screw principle. So mathematically, if you want to express this, we have said its magnitude is equal to the product of magnitude of A, magnitude of B, and the sine of the angle between them. So if the angle between them is theta, okay, then the magnitude is given as, sorry, the product is given as A cross B, that is magnitude of A, you write it this way, the magnitude of B, then the sine of the angle between them, sine theta AB, multiplied by the unit vector an. So this unit vector gives the direction of the product vector. Okay, so n stands for normal direction. So the n is in the direction that is perpendicular to both a and b. And how do you determine which direction? You can determine the direction by using this right-handed screw principle. So this is that right-handed screw, as we have seen. If you place if there are if these are two vectors, this is vector a and vector b, the angle between them is theta ab. So if you place a screw here and rotate the screw from a to b, what is the direction of advance of the screw? Means which in which direction does the screw move? So if you place it, if this is a horizontal plane, if you consider this as a horizontal plane, and if you place the screw perpendicular to that plane and rotate it from A to B, the screw will obviously move downwards, right? The screw will obviously move downwards. So the direction of the product vector A cross B is downwards, as it is shown in this figure. Okay. So also you can use your right-handed rule, as we have seen in the coordinate system. So if you take your forefinger as vector A and middle finger as vector B, then the thumb finger, the direction of the thumb finger, when you hold this like this, it will give the direction of the product vector A cross B, right? So this is about the expression for the cross product or vector product. The cross product is also called the vector product. But as we have seen, the dot product was commutative. That is, the order of A and B did not matter when you wrote the expression. But in case of cross product, it is not commutative. That means A cross B is not equal to B cross A. Okay, but in fact, why it is not equal to B cross A is, one reason is it is a sine function. Sine function is not an even function. Sine function is an odd function, right? In dot product, we had cos. It was an even function. That is, cos of minus theta is also equal to cos theta. But in case of sine function, it is an odd function. That is, sine of minus theta will be equal to minus sine theta. So that is why if you reverse the order, if you take B cross A, it will not be equal to A cross B, but in fact it will be equal to minus A cross B. That means it will be equal in magnitude but opposite in direction. Okay, it will be equal in magnitude but opposite in direction. So you can take it from the example of this right-handed screw also. If you move the screw from B to A, the direction will be upwards. If you move the screw from B to A, the screw will move upwards, not downwards, right? So it is in the opposite direction. So that is how you determine the cross product or the vector product. Now, where do you use this cross product? So why we are going to study this cross product? So one example where we use it is in trigonometry or in geometry to find the area of a parallelogram. The area of a parallelogram is actually given by the product of its adjacent sides. Okay, product of the lengths of two adjacent sides along with the sine of the angle between them. So the product of two adjacent sides, if the sides are A and B and the angle between them is sine theta, then it is nothing but the product, the cross product. The magnitude of this cross product will give the area of parallelogram. If you just consider the scalar area, it will you can just take the magnitude of this A cross B, that will be the area of the parallelogram. One more example or application where we use this cross product is in magnetic fields to find the force on a straight conductor of a particular length L. So the force on a straight conductor is given by this equation. We are going to derive this when it comes to magnetic fields. That is given by I into L cross B, where L is the length and B is the magnetic flux density. Okay. So here again, it will follow the same principle. If the direction of the current is indicated by forefinger and the middle finger indicates the direction of magnetic field, then the force is given by the direction of the thumb. Okay, because it's cross product. One more important application is to find the power density, okay, or the energy flux density, that is Poynting vector, that is given by Poynting vector. We are going to study this in the last module. That is given by S, that is the cross product of electric field and magnetic field, E cross H. Okay, cross product of E cross H will give you the power density, in fact, that is again obtained by the cross product. One more example which you might have studied in physics, to find the torque. The torque is given by R cross F, where R is the radius and F is the force. Okay, so that R cross F, it can be given as RF sine theta. Okay, this is nothing but the torque. Okay, this is actually the cross product. R cross F will give you RF sine theta, and using this thumb rule, we can get the direction of the torque. And one more thing where we are using this when it comes to this particular subject is to find the curl. Okay, curl is expressed as del cross a particular vector. Okay, I forgot to mention yesterday we use the dot product to find one thing called divergence. Throughout the subject we are going to use that when you perform dot operation on del. Okay, we are going to get divergence. When you perform cross operation on it, we are going to get the curl. So we will deal with this when it comes to those particular topics. So next we will take into consideration the unit vectors in rectangular coordinates. We have x, y, and z. All these three, they are mutually perpendicular to each other. So the angle between them is 90 degrees. So we have taken a similar case into consideration with the dot product. We will do the same thing for the cross product. The angle between x and y, ax and ay is 90 degrees. Similarly, between ay and az it is 90 degrees. Also between ax and az it is 90 degrees. So what is the cross product of two vectors, two unit vectors, ax cross ay? So following the definition, we have a magnitude of ax multiplied by magnitude of ay multiplied by sine of the angle between them. The angle between ax and ay is 90 degrees because they are perpendicular to each other, multiplied by the direction. What is the direction when it comes to ax and ay? If you follow that right-handed screw rule, if you place the screw here and rotate the screw in the direction of x to y, from x to y, the screw will move upwards. This upward direction is nothing but z direction. So the direction of the product vector will be az. Okay, so the magnitude of ax is, it's a unit vector, so it is 1. Similarly, magnitude of ay is 1. Sine 90 is again 1, right? That's why what remains is only az. Okay, product of two unit vectors is obviously another unit vector, and the direction is the another coordinate. If you take x and y, the product will be in z direction. Similarly, if you take y and z, their product will be in x direction. If you take z and x, their product will be in y direction. Okay, so it's very easy to remember. Now what if you take it in the opposite way? What if you take ay cross ax? Can anyone tell me what is the product of ay cross ax? Okay, so if ax cross ay is az, ay cross ax will be minus az. Similarly, az cross ay will be minus ax, and ax cross az will be minus ay. Okay, so it's given here. So this thing you can remember it as it's in a cyclic order. It's in a cyclic order. Yeah. If you take ax cross ay, the answer will be az. If you take ay cross az, the answer will be ax. If you take az cross ax again, the answer will be ay. Okay. But if you take the order in the reverse way, if you take it in a reverse way, the products will be negative. That is, the direction will be opposite. Okay. So you can remember this in a cyclic order like this. Then what if you find the cross product of a vector by itself? The angle made by ax with itself is 0. So here we have the sine operation. Sine 0 is 0. That's why cross product of a vector on itself is 0. So yeah, ax cross ax, ay cross ay, and az cross az is 0. So now we will use those things here. We will take two vectors. Consider there are two vectors in rectangular coordinates, a and b. So a you can express as ax plus ay plus az. Here capital Ax, ay and az are the components of this vector a in x, y and z directions. Similarly, there is another vector b, which is bxax plus byay plus bzaz. So bx, by and bz are the components of this b in x, y and z directions respectively. Now we are supposed to find the cross product of a and b, a cross b. So how do you get this? So you can use the distribution theorem and multiply each term of a with each term of b. Okay, so since there are three terms on in both the vectors, you will have a product which has 9 terms, sum of 9 terms, right? So it is this first term multiplied by first term of b, first term of a multiplied by second term of b, first term of a multiplied by third term of b. So that way I have got this. Okay, so ax cross bx to perform the cross operation similarly. Then you take the second term of a and multiply with each term of b. So you will get this particular thing. Then you take the third term of a and multiply with each term of b. Third term is az, multiply with bxax, take the same thing, multiply with byay, and take that and multiply with bzaz. So you will get a term which has the product which has 9 terms, the sum of 9 terms. Now what you do, this cross product is it is working only on vectors. So you separate the scalar parts and vector parts. You can take it like this: ax bx multiplied by ax cross ax. Similarly, in all the terms you do that: ax by multiplied by ax cross ay. Okay, scalar terms you keep it aside and vector terms you separate from them. So if you do it for all the 9 terms, you will get this. Now you know the cross product of unit vectors, right? What is ax cross ax? Ax cross ax is 0 because the angle between ax and itself, it is 0. So this term is 0. Similarly, ay cross ay becomes 0. Similarly, az cross ax becomes 0. Now what about the remaining terms? Ax cross ay. Ax cross ay is ax cross ay is the third vector, that is az. What is ax cross az? Ax cross az is minus ay. Yeah. What is ay cross ax? If ax cross ay is az, ay cross ax will be minus az. What is ay cross az? Ay cross az is ax. Az cross ax is ay, and az cross ay will be minus ax. Okay, so taking these products Yeah, you will get this. The same thing, it is written again, ax by into az plus ax bz into minus ay bx into minus az. The same thing, I have written it again. Next, you group the unit vectors in terms of ax, ay, and az. Ax, there are two terms. Yeah, ay bz minus az by. For ay, two other terms. Yeah, az bx minus ax bz. Az, there are two terms, ax by minus ay bx. So now, this is nothing but the expression for the determinant, right? It's a determinant of A cross B with three rows and 3 cross 3 matrix. It's a 3 cross 3 matrix, determinant of that particular matrix. Ax, Ay, Az is the first row. Next, capital Ax, Ay, Az, that is the components of this vector. First vector, it is the second row. Then the second vector will be the third row. Bx, By, Bz will be third row. So you know how to find the determinant of a matrix, right? So it's similar. If you find it, you get the same expression, right? So the first, the first term will be ax multiplied by ay bz minus this thing az by. You have studied this in maths, right? And also maybe in linear algebra last semester. Minus ay multiplied by this thing ax bz minus az bx plus az multiplied by ax by minus ay bx, right? So if you compare these two expressions, it is one and the same. So ax in the terms of ax, will be y and z. The terms for ay will be z and x. So you have a minus here, right? So minus ay ax bz. That's why you have a minus ax bz, and positive will be az bx. So minus into minus will give you plus. So that is how you get it. Next, for az you have ax by minus ay bx. So it's one and the same. That is why in a simple way you can represent the cross product of two vectors as the determinant. Okay, determinant in this way. The first row will have the unit vectors. Second row will have the components of the first vector. Third row will have components of second vector. So we will take an example of two vectors, a numerical example with these two vectors a and b. A is given as 2ax minus 3ay plus az, and b is given as minus 4ax minus 2ay plus 5az. So how to find the cross product of these two? You take the determinant and do it, a cross b. Okay, so a cross b is this particular thing. Now tell me, what is ax, ay, az? Yeah, ay and az minus 3, 1. Similarly, what is bx, by, bz? It is minus 4, minus 2, and 5.
Minus 4, minus 2, 5.
Okay. So you rewrite this particular determinant with these terms. Okay. In place of these components, you substitute these terms, these values, and find the determinant. So if you find the determinant, what do you get? So you will get the product. So what I want to show is the product will have the direction. Unlike the dot product that we had, this will not be just a number. It will have ax, ay, and az components. So that means it is another vector. Okay. So if you multiply, or if you find the determinant, so you will get it like this. Okay, minus ax into minus 3 into 5 minus 1 into minus 2, ay into 2 into 5 minus 1 into minus 4, az into this thing, 2 into minus 2 minus 3 into minus 4. So if you simplify, you can do that. You will get this minus 13ax minus 14ay minus 16 Az. So that means it has got a particular magnitude and the direction. And the magnitude of this, it is obtained by, you can use that square root of minus 13 square plus minus 14 square plus minus 16 square. That will give the magnitude of the product. And this expression will give the direction. Okay. The unit vector in this direction will give the direction of this particular product. Okay, so that's about the cross product. We have seen two types: dot product, which gives actually the scalar product, and the cross product, which is actually the vector product. So in the next part, we have one interesting thing, that is, there are two other coordinate systems that we are going to study. We have already seen the rectangular coordinate system or the Cartesian coordinate systems, which we are already familiar with. There are three axes, x, y, and z axis, right, which are mutually perpendicular to each other, and each plane, we can see each point as the intersection of three planes, and each plane is a, yeah, each surface, intersection of three surfaces. Each surface is a plane in case of rectangular coordinates. But in every case in electromagnetics, the rectangular coordinates, considering rectangular coordinates, will be very tedious task. If you want to express everything in rectangular coordinates, it will not be so easy, because what we are going to consider are different kinds of charges, including a point charge or a line charge or other things, right? So there we are trying to exploit the symmetry. So when you take a point into consideration, okay, so a point is nothing but a sphere of radius 0, right? You can consider a point as a sphere. You know what is a sphere, right? A ball, right, of a constant radius. So a point is a sphere with radius 0. So if you want to consider a surface which actually encloses this point, you need to consider a spherical surface. So when you consider rectangular coordinate systems, it will be a tedious task to express or try to get the symmetry of this particular point. Yeah, that's why we try to, or we use another coordinate system called spherical coordinate system. And apart from this, there is one more coordinate system, that is cylindrical coordinate system. So if you consider a line, okay, if you consider a line, so line's symmetry is not along the rectangular coordinates. Its symmetry, it is along a cylindrical coordinates. It is more like a cylinder. A line can be considered as a cylinder with radius 0, right? So a cylinder is nothing but, there is a body like this, and yeah, it has a certain base, maybe circular base, right? So if in that circular, if the radius is 0, you get a line, right? So for this particular case, we consider cylindrical coordinates. Again, in cylindrical coordinates, there are different things like circular cylindrical coordinates, elliptic cylindrical coordinates, parabolic cylindrical coordinates, but we are considering only circular cylindrical coordinates, where the base of the cylinder is a circle. Okay, so this we will see in the next class. We are going to have a circular cylindrical coordinate system and spherical coordinate system. Here again, there are three axes, just like x, y, z. There are three axes in rectangular coordinate system. Here we have three different axes in circular cylindrical coordinate system as well as in spherical coordinate system. So we will continue in the next class.